Hi, this is an example problem, coal versus nuclear fission, which compares the energy content of coal versus nuclear fission for domestic energy production. So it says we have 1 kilogram of coal is burned, approximately 3 times 10 to the 7th joules of energy released. That's for 1 kilogram of coal. For uranium, a single fission of a uranium-235 nucleus produces about 200 mega electron volts on average. The question is, how many kilograms of coal must be burned to produce the same energy as 1 kilogram of uranium-235? So first of all, since we know the energy per individual uranium-235 nuclei, we need to figure out how many nuclei are there in 1 kilogram of uranium-235. So we're going to try to answer this question. Well, we're going to start out with 1 kilogram of U-235. And now we're going to try to convert that to the number of nuclei that are present there. To do that, we need to figure out what is the mass of a individual uranium nuclei, and then we can do this conversion here. Well, we're given in the problem, or we could have looked this up in Appendix F, the molecular mass of uranium in units of AMU. Now, to be able to convert from kilograms, 1 kilogram, to units of U, or AMU, we need to go ahead and look up a conversion for that. So this sheet here that I have for nuclear reactions gives you some brief notes about nuclear reactions. If you go to the next page, it gives some useful conversion factors. And in particular, here is one that we can use here. This is a conversion from U to kilograms. And we can go ahead and use this little conversion here to do this step. So let's go ahead and let's get rid of the kilograms. So we're going to put that on the bottom, 1.6605 times 10 to the minus 27 kilograms per 1 U. Okay, good. So that's going to give us total U of the mass of the sample. And now we're going to go ahead and convert that into particles using the molecular mass there. So we have 235.0439301 U per particle of U-235. Of course, we can cancel out the U's here, and we're going to be ending up with units of particles. We end up with 2.562 times 10 to the 24th particles. And that sounds pretty good because it's a large number, you know, quite a bit more than 1 mole. And for a kilogram, that sounds pretty good. Now we need to go ahead and see how much energy can be generated from those particles. So we're going to assume that every single one of these particles undergoes fission, and in doing so, each of those particles releases a certain amount, on average, 200 mega electron volts per fission. So let's go ahead and do one more unit conversion here. That many particles of U-235. And now for each particle, we're going to get 200 MeV of energy released. And of course, we're going to cancel our particles out, and we're going to end up with the total energy released if you fission completely 1 kilogram of uranium-235. Which comes to 5.124 times 10 to the 26 mega electron volts. Now what we want to do here is convert this to joules, because the energy of the coal is given to us in joules. So let's go ahead and just do another conversion. This whole problem is just unit conversions essentially, right? We're going to take this energy, we're going to convert it to joules. So this conversion here. We can go back and look at our notes if we want. 1 MeV is 1.60 times 10 to the minus 13 joules. I cancel our MeV out and we'll be left with joules, which comes out to about 8.20 times 10 to the 13th joules of energy. And again, remember that this is per 1 kilogram of U-235. Now, how much coal are we going to need to be able to burn to generate that same amount of energy? Well, we know that the coal for 1 kilogram is 3 times 10 to the 7th. Okay, so we can go ahead and take this energy number here. I'm going to start with 8.2 times 10 to the 13th joules of energy. And we have 1 kilogram of coal produces 3.0 times 10 to the 7th joules. We'll cancel our joules out and we'll determine how much coal would need to be burned. This comes out to about 2.73 times 10 to the 6th kilograms of coal. So it's a little more than 1 million times the mass of coal is required to produce the same energy of 1 kilogram of uranium if that uranium was pure U-235 and it all fissioned. This is pretty normal because nuclear energies, their reactions are usually, 1 million times more energetic than a atomic, electron changing chemical reaction that coal undergoes. Of course, in a real fission plant, if you're using uranium, actually U-235 in the plant is only about 3 to 5% of the total uranium. So there's a lot of other isotope in there. It's only that 3 to 5% uranium that actually goes towards fission. Moreover, naturally mined uranium is only about 0.7% U-235 by composition. And so, as you're probably aware, the uranium needs to be enriched with U-235, which they use centrifuges to do, to get the 3 to 5% so that it can be a viable fuel for a fission power plant.